it says participants can now see your screen. So
yeah, so I can see the slide editor, and you're showing the Pythagorean /
yes.
Burrau's problem. Okay.
Okay, maybe I'll just do it this way. Thank you. Yeah, so here on the right, you can see this triangle, which is the initial condition for a chaotic three-body problem, which consists of a triangle with sides 3, 4, 5, and the masses are placed at the corners of this triangle, and they also have masses 3, 4, and 5. And this initial condition was introduced over 100 years ago and first solved with pencil and paper. And then later in the 60s, with the advent of computers and body simulations, it was solved on a computer. And ever since, it's a nice textbook example of a chaotic triple system. And its solution, which is very generic for chaotic systems, looks a bit here like on the right, where each color is a different orbit for a different body. And you see this chaotic interaction, these chaotic orbits in the center, which is basically a series of ejections. Then you get close to the center again, you interact, and you have another ejection, etc. And this has a certain duration, after which there is a very close encounter among all three bodies, such that one body escapes. In this case, it's the lightest body, which escapes towards the top right, and the binary escapes the other way. So this is a generic outcome of an unstable triple system. And you can see by eye it's chaotic, but it would also be good to quantify that a bit more. And one way to do that is as follows. You take the unperturbed initial condition and you evolve that forwards. And you can also take a perturbed initial condition, where you take one coordinate of one body and you slightly perturb it. And then you evolve that one forwards. And then you can measure how those two solutions grow apart as a function of time. And that's what I show on the next slide. So the top equation basically gives the phase space distance in 6n dimensional phase space, where n is the number of bodies and 6 is the 6 phase space coordinates. And in the plot, you can indeed see the log of this separation as a function of time, where I introduced a small perturbation of 10 to the minus 10. And we can see after about 30 time units, it goes up rapidly, exponentially, which confirms this exponential sensitivity in the three-body problem. And at around T60, the binary and single configuration is achieved, which is stable, and we can see that the growth is much slower. In fact, it becomes linear. So two things we can measure from this complicated plot are the range on the x-axis, which is the lifetime of the triple interaction, and the range on the y-axis, which is the amplification factor. So the initial perturbation is only 10 to the minus 10. So it's a perturbation in the 10th decimal place. But it grows within the lifetime of the interaction by about 8 or 9 orders of magnitude. So this gives the log of the amplification factor. And so depending on your initial condition, you get different lifetimes and you get a distribution of the amplification factors. Another thing you can measure is the following. We know Newton's equations of motion are time reversible. So if we at t is 100, we integrate back, or equivalently, we can change the sign of the velocities and integrate forwards for another 100 time units. Do we retrieve our initial condition, yes or no? And that's what we do here. So if we first look at the blue curve, which has a certain accuracy and precision for the embodied code, which is shown here in the legend, you can see indeed the two solutions are approaching, but at some point there's an inflection point after which their separation grows again. So the two solutions, they try to find each other again, but there are these numerical errors which grow as a function of time. And these numerical errors are not time reversible. They keep growing. So at some point, the two solutions don't know which way to go to find each other again. And so unavoidably, they will go apart again. Now, if you systematically increase your accuracy and your precision, so this is an embodied code I've written, which is very, very precise. You can set the discretization time scale by a certain tolerance, which really goes beyond standard precision. So in this case, I go all the way to 10 to the minus 24 precision. And you can set the word length, which is the number of bits which I use for my operations. So I go beyond double precision. You can find if I crank up my accuracy and precision, this inflection point is delayed until I find a time symmetric or time reversible solution. So depending on the magnitude of my time irreversible fluctuations, I can either find my way back or not. Now I want to measure these things not just for one triple, but for a population. So one way to make a population is as follows. It's called the Agekyan-Anosova map, where you place one body at point A and one body at point B, and then randomly you put a body within this region. So here on the right, each dot is a different initial condition, a different simulation. And in this case, color-coded is the lifetime of the triple system. You can see chaotic regions and more coherent regions in there. And so by taking this map of initial conditions, I can measure the distribution of amplification factors and determine for a given magnitude of the fluctuation, am I time reversible or not? And then I get to my main result, which are these two power laws. So here on the left, I show the fraction of irreversible triples as a function of the magnitude of the small perturbations. And so in the limit of infinitely small perturbations, I go all the way to the left, then the fraction of irreversible systems will go to 0. So I retrieve Newton's time reversibility. However, if there is a small fluctuation, time irreversible fluctuation of order epsilon, there is a power law tail beyond which triple systems live, which are irreversible. And it turns out these two power laws are related. On the right, I show the distribution of amplification factors. And for the Pythagorean problem, it was only about 10 to the 10. But there are triples out there with amplification factors 10 to the 30, 40, 10 to the 70, and beyond. And so this shows that in my population, there are very, very chaotic triple systems, which basically live for a long time. And within their long duration, they keep exponentially magnifying these small perturbations to very large sizes. So if we now apply this result to, let's say, 3 supermassive black holes, we have 3 times 1 million solar mass black holes with a mutual separation of about 1 parsec, 0 angular momentum. We find that the Planck length would be about epsilon 10 to the minus 50 in my plot, which means that about 5% of my triple systems would require an accuracy smaller than the Planck length in order to go forwards and backwards again. In other words, this 5% of triple systems are fundamentally unpredictable. Now, what happens if I add relativity? Because up so far it was all Newtonian. So if you add relativity, other things can happen. Like in this case, on the left, you see the global picture of a chaotic triple. But there's a small black box over here where 2 of the bodies had a very close encounter. And if I zoom in, you get the plot on the right. And you see it was a gravitational wave capture, after which there's an in spiral, and these 2 bodies will eventually merge. So you get gravitational wave emission and precession. And if you do this for the Pythagorean problem, so there's one triple again, but I systematically vary the strength of the relativistic effects, which I do by vary the mass scale. So I fixed the 3 black holes to separates of 1 parsec, but I fixed the mass scale, or I changed the mass scale on the x-axis, and then I measure the lifetime. And what you see is that on the top left, relativity is very weak, as you basically retrieve the Newtonian solution. But then at some point, the small relativistic perturbations are magnified due to the chaos, which causes this chaotic noise, whereas a small change causes a big difference in the lifetime, until you reach a mass scale of order a few times 10 to the 6, 10 to the 7. And that's when the gravitational wave emission starts to kick in, and you systematically produce mergers, even though there's one blue dot over here, which signifies ejections. And so this plot shows very nicely that below this transition point, you mostly have unstable triples which dissolve into an escaper and a binary, whereas beyond this mass scale, you mostly produce mergers. So the takeaway message is twofold. One, Newton shows there's the theoretical existence of fundamentally unpredictable triple systems, which could be black hole systems. When you add relativity, there's an interesting transition from ejection to merger-dominated dynamics. And so these chaotic triples could be interesting formation channels for gravitational wave sources. And that's all. Thank you very much.
Okay, thanks very much. I think we do have time for a quick question if anybody has one. I guess one question which I have is, and so you obviously show that you get these capture mergers occurring. Do you have any idea what kind of rate you would expect to see that sort of thing happening at in the galaxy or in the universe, or is that just, I guess your work is entirely about the simulation side of things, but have you put any thought into how likely it is that we will actually see one of these?
Yeah, that's a very good question. So these chaotic triple systems, they are thought to occur inside star clusters, so globular clusters, open clusters. There's also a lot of recent work about galactic nuclei. And so you can have these binary single encounters in the Agekyan disk. And these are generally chaotic. One of the black holes can get ejected, they return, the whole configuration changes until you reach a binary configuration with such a high eccentricity that you can have these gravitational wave captures occurring. There are some, the dominant dynamical formation channel for gravitational wave sources are still a topic of debate. There are some studies which say that the triple systems in globular clusters can explain the observed rate. But yeah, it's still a topic of debate. But chaotic triple systems definitely seem to contribute a significant amount.